give you a talk today about physics breakthroughs last year. When I received the invitation to give you a talk here, I had to think for one day, what should I tell you about what should I speak in front of you today? It was a very difficult decision because I took into consideration two things mainly. One, that you are children, and two, that you are gifted. So these two criteria were a little bit divergent. And I thought to tell you about something interesting about science, but not to go very deep into mathematics or, I don't know, very difficult processes in front of you. After a while, I arrived to this conclusion that I should tell you something about what happened last year. Because each year in science, and especially in physics, because you are physics lovers, a lot of things happen. So from time to time it is very useful to take a step back and check what happened in the meantime. So the third point I had in mind when I decided to give this title was that in general science is the engine of prosperity. Until not very long ago, everybody told in public that science will be the future of humanity, but as you can see now, you cannot leave the house without your phones and without your loved gadgets. We are in that era. So the present is something belonging to science or technology. Seeing technology, engineering as applied science. That's why I proposed this title. After sending the title to the organizers, I thought, why talk about only the breakthroughs or the successes obtained last year in science? Let's talk about some words. Let's tell some words about some events taking place last year, which are related to physics or which belong to physics. And because it is about 2018, I started from 18 and I decided to present you 2 times 18 facts from last year, so 36. And I will present just the facts without making a lot of comments. And then I will focus on one of them. I hope that the presentation will be short enough. You should translate this by, last night was not long enough for me to finish the presentation. So let's start. I tried to group the processes and the successes and the events of last year on some topics. I chose the topics, I named the topics after I gathered the events. So the first topic is optics and laser physics. And from last year, I kept only 3 things. Finally, in 2018, the researchers at Harvard reported that they realized the first lens without aberrations. So what was used until then and even now, in order to obtain a good image, you have to use more lenses. Not only one, because only one lens will present aberrations. So the image will be deformed. We'll get different colors, not the real ones all over the image, but they reported that they realized the first single lens that can do what a bunch or a stack of lenses used to do. The second thing is that the physicists in Quebec, in Canada, from the Institut National de la Recherche Scientifique, as it is called in French, they realized the world's fastest camera until now. It can take 10 trillion frames per second. That type of camera is very useful when we are analyzing very fast processes, because we can look at those processes afterwards, frame by frame, and realize the logical succession of physical processes. So we can see more details than ever using such fast cameras. And of course, this was a success also, but an event. Arthur Ashkin from the United States, Gérard Mourou from France, and Donna Strickland from Canada won the Nobel Prize for Physics last year for groundbreaking inventions in the field of laser physics. That quote is from the Nobel Committee. Perhaps about Gérard Mourou, some of you heard already. The Romanians, I think, maybe have heard about him because he is very involved with a huge company in France called Thales. I think for Eastern Europe it has the headquarters in Bucharest, and that is the only company making powerful lasers. In Romania there are 2 lasers installed by Thales, and the other 2 in Eastern Europe are installed in Hungary and in Czech Republic. They are the most powerful lasers in the world these days. Certainly you've heard, or maybe you visited the Institute for Nuclear Physics and Engineering near Bucharest, where the ELI facility is installed, and that is the most powerful. It has 3 heads, each of them able to deliver 10 petawatt. This is a huge power. In the same area, there is though another laser of 1 petawatt power in another institute on the same platform, a research platform near Bucharest in Măgurele. It is called CETAL, and that laser is a kind of playground for the big one. So scientists all over the world can come to that facility at the National Institute for Plasma, Laser and Radiation Physics. That's where the CETAL is installed, and can try new experiments to see what happens at 1 petawatt, and if the results are promising, or if they cannot successfully decipher what's going on in there, they can go and make the same experiment at ELI. So the powers nowadays are huge in laser physics, and the results are spectacular. And because we are here and I talked to you about the unprecedented values for the powers in lasers, for the number of frames in the new cameras, I wanted to give you this talk just for you to see that science is moving very, very fast ahead. So science is not reduced to only what you learn in school and what you see on television, although lately a lot of more and more scientific programs run on different TV stations. So you can have the opportunity of your age to witness the great breakthroughs in science. Well, the next field is related to biophysics and medical physics. And here I wanted you to learn, or for some of you to learn only 1 or 2 of the breakthroughs I put here only 5 successes of last year. First, the first one is related to the creation of an artificial muscle for shape-changing cell-sized robots. So they are tiny robots, but they needed special muscles to make them move. And the muscles should change their form and their geometry. They have a lot of applications starting from the medical field towards research in the outer space. So they have to be able to realize and to produce artificial muscles able to move the entire body, the entire robot. Well, meantime in Europe, at the Technical University in Munich, the researchers there reported a new propulsion method for molecular machines. So they are also tiny. Their dimensions is comparable with those of biological cells. So they are very small. But what is interesting here, because such machines were reported before, what is here very important is that they are 100,000 times faster than the biochemical processes taking place naturally inside the human body and in living organisms. So they are very fast. Well, in the field of medical physics, there are two other successes last year. One is the realization or the producing the first artificial corneas, which is a part of the human eye, and also the first artificial iris. And finally, this is the same as before. I forgot to, I told you that the night was too short. In the field of low-dimensional material physics, there is an entire field which is very active nowadays, searching for different characteristics and for special properties of materials which are low-dimensional, which means that they are not 3D, they are more like 2-dimensional, which are sheets or layers, very thin, or they are rods or threads. They are linear. They have 1 dimension, and in some cases, for example, for quantum dots, they are 0-dimensional. They are almost like dots. So, the researchers in MIT devised a new method to create stronger and more resilient nanofibers. This kind of fibers, the new ones produced, are many orders of magnitude stronger than the metallic ones we know from our day-to-day life. And that they can have a lot of applications in different areas of science. I was pleased to see that the engineers at the University of Texas in Austin and the physicists from the Peking University in China continue to collaborate. They started this collaboration more than 20 years ago. And they announced the creation of a new device, kind of memory storage device, a new type, which is now only 1 atom, having the thickness of 1 atom diameter. So they have only 1 layer of atoms. And despite this very narrow thickness, they have an enhanced ability to store data. And they call it atom resistor, for joining 2 words, resistor or transistor and atom. And another breakthrough was that the researchers of MIT developed a new and more efficient method to produce layers of graphene which are longer than usual. Of course, many of you know what graphene is. Yeah, it's a monolayer of carbon atoms having special properties, totally different than the properties of carbon in graphite, which is the commonly encountered state of existence. And as you will see later, they will discover new properties for these graphene layers, also last year. In the field of astronomy and astrophysics, a lot happened last year. From what happened, I chose only a few of them, 5, if I didn't repeat anything, and I think not. Researchers found some additional evidence for an exotic form of water called superionic water, which is not found naturally on Earth, but could be common on planets like Uranus or Neptune. Because if you want to study the properties of matter on these planets, we have to understand first what happens at their surface and what kind of properties have those materials and how different are they for the materials which are similar and we can find them on Earth. Towards the end of the year, I put the day and the month there. Probably you've heard on the news that on the 5th of October, the Hubble Space Telescope was hit by a mechanical failure, and it lost one of its gyroscopes. You know, a gyroscope is a device, a mechanical device, so in a fast rotation movement, which points towards the same direction, which preserves the direction. And it was used for orientation in space. So in that case, the Hubble Space Telescope was placed into a safe mode, idle mode, until the scientists will fix that problem and make the telescope behave normally again. Well, in the same month, at the end of it, NASA made another announcement informing us that the Kepler Space Telescope finished its fuel. So this happened after 9 years of service. And during these 9 years, the Kepler Space Telescope helped scientists to discover more than 2,500 exoplanets. We can say that the Kepler Space Telescope did its job. So, under these conditions, NASA announced that the Kepler telescope is officially retired, and it will maintain its current and safe orbit around the Earth, but at a very big distance. Another important thing is that astronomers confirmed the existence of dust cloud satellites called Kordylewski's clouds in the 2 regions, L4 and L5, which are some Lagrangian points of the Earth-Moon system. You saw the positions of the Lagrange points. I will give the presentation afterwards. That was a piece of big news, and also scientists reported that they succeeded to detect the nature ice 7, a special state for ice, on Earth, not on other planets. Previously it was thought that it can be produced only on the moons of Enceladus, Europa, and Titan, the satellites of Jupiter. But on Earth, they produced it until now only artificially, so with the help of the scientists. But now they detected it in a natural state. You know, computer science evolved and developed only because physicists and the engineers produced the technology necessary to make microchips and to make memory devices and all the circuitry necessary for the computer to run. Now, everybody's attention is concentrated towards quantum computing and neural computers. So to find new methods to make computer faster than ever before, and the results I kept for showing you are three. So the engineers at MIT developed a new computer chip with artificial synapses, like the neurons in our brain, which process information more like neurons and not like in microchips until now. Of course, the signal is also an electrical one, an electromagnetic one, but the way in which the information is transmitted and processed is very close to that, the same process happening in our brain. And about quantum computing, they discovered last year a new form of light which may involve polaritons that could be useful in developing quantum computers. The polaritons are some quanta of polarization. So it is a strong, it represents a strong connection between an electromagnetic field and an electric dipole. And the quanta for polarization is called polariton, and there is a lot of mathematics describing them, which is very advanced, and there is no need for us to go into details right now. And the third breakthrough was achieved by the scientists, by some scientists at the University of Alberta, Canada. They reported a new technique, which is very interesting because it is based on quickly removing or replacing single hydrogen atoms, which can provide a 1,000-fold increase in solar state memory density, which is something unexpected. So to increase for 1,000 times the density of information you can store is something huge. Now in the field of superconductor physics, well, a new property of graphenes was, as I was announcing earlier, was studied, and it acted as a superconductor, which is very interesting. And that layer of graphene is acting like a superconductor only when some of its atoms are rearranged. Because usually the graphene has hexagonal order, but when some of its atoms are rearranged in that matrix, in that structure, the layer changes its behavior. And of course, the quest to obtain superconductors at room temperature continues. And the success of last year was that a group of physicists reported the discovery of superconductivity at 250 Kelvin, which is very close to 0 degrees, but at high pressure, 170 gigapascal or gigapascal. In quantum physics, the physicists reported for the first time producing quantum entanglement using living organisms, particularly between living bacteria and quantized light. Quantum entanglement is an interesting property in the quantum world, which basically is about studying a group of quantum particles and it doesn't matter if they are close or far from one another. One of the states of one particle influences the state of the others. So they are related among them. This is this is how the word entanglement arises, basically. And also physicists reported that quantum behavior can be explained with the help of classical physics, but for one particle. For more than one particle, as in quantum entanglement already mentioned, and all other related non-locality phenomena, it is not possible to give an explanation with the help of classical physics. I put there the name given by Albert Einstein to non-locality. He termed it spooky action at a distance, but in German. Well, in the field of high-energy physics, also, last year was a rich one with a lot of results, and I put 5 of them for you to see today. The first one is the detection of a stronger neutrino oscillation, a stronger signal than expected, than usual, which is a possible hint, or so they said, of a sterile neutrinos, which is an elusive particle that may pass through matter without any interaction. It's very hard to detect. There were 2 results, the second and the 5th one, related to the Higgs boson, which made all the headlines in the year they discovered it. The first one is the direct coupling of the Higgs boson with the top quark, observed for the first time in the ATLAS experiment and the CMS experiment at CERN. And maybe you read more if you are interested of any of this news. You can read more on the internet to see more details and to understand more about what happens related to this news. And also they reported, they observed the decay of a Higgs boson into a pair of bottom quarks, which is an interaction that is primarily responsible for the natural width, it is called, of the boson, which is the interval in which you can find the mass, the value of its mass. Other breakthroughs happened at the IceCube Neutrino Observatory, which announced that the researchers there have traced a neutrino that hit their Antarctica-based research station, but in September 2017. And they think that it arises from a very distant star, many 3.7 billion light years away. And it is the first time that a neutrino detector has been used to locate an object in space. And also the scientists announced the transformation of a gaseous deuterium into a liquid metallic form. So this may help researchers to understand better giant gas planets, such as Jupiter or Saturn, and some other related exoplanets. And why it is so important? It is because it is thought that this liquid metallic hydrogen is responsible for their observed very powerful magnetic fields. Well, in the field of plasma physics, I kept only two information. Both of them are related to plasma fusion, which is the processes, which is a huge chain of processes which eventually will enable us to obtain clean energy. So one breakthrough is related to the success in controlling some edge localized modes in tokamak devices, which is a huge facility. I wrote there, without creating more problems. The main problem related to fusion is that inside a fusion device, there are a huge number of instabilities, so we cannot fully control the plasma inside and what's going on in there. We want to fully control it in order to operate such a facility. And last year, they reported such a result, and also China's Institute of Plasma Physics from Beijing announced that in their experimental advanced superconducting tokamak, which is a huge device there, they reached 100 million degrees Celsius. Now in the field of geophysics, researchers reported evidence of rapid shifts. Rapid means very fast, but in geological terms, not in our day-to-day life, time intervals. Nearly 30 times faster than it was known previously, of the reversals of the magnetic poles. And this discovery included also a chronozone, which is a zone of events taking only 200 years long, which is very short on geological time, and is much shorter than any other reversal found until now. Well, about the green energy and the environmental physics, a study with a lot of calculations made by the researchers at the University of Illinois at Urbana-Champaign find that large-scale solar panels and wind turbines could transform Sahara Desert. And this will have, or would have, a major impact on rainfall, vegetation, and temperatures, potentially greening that region. You know that in the west of Sahara region is the area where all the huge storms hitting the United States are formed because of the high temperature in there. And they will go across Atlantic and hit Florida and all the states around. So if they manage to change the Sahara Desert, those huge and very costly in human lives and in damages across the coast of the United States will be reduced significantly. Also, another success, which seems not much, but it is huge for photovoltaic cells, for solar panels, is that last year the efficiency of those panels increased 2.5%, which is much because until last year the most efficient solar panel was 15%. So this is the real efficiency of transforming the solar energy into electric energy. And finally, the researchers in Brazil succeeded to describe a new two-dimensional, so a low-dimensional material, which they called hematen, with having the properties close to the hematite we have in our bones. And it is used, and it will be used as a photocatalyst. So to start some chemical reactions and to produce new chemical products. In the field of material physics, I put this information here Although I could put it in any different previous slides regarding low-dimensional systems and so on. The scientists of Sandia National Laboratories in the United States, they produced a platinum gold alloy, which will be more resistant than any other metal used in applications nowadays in the world. And they evaluated that it will be 100 times more durable than high-strength steel. And finally, this is the 36 information about what happened last year. On the 16th of November, at the 26th General Conference on Weights and Measures, everybody voted to revise the definitions of the International System base units or fundamental units, which the International Committee for Weights and Measures had proposed earlier, also last year. And the new definitions came into force this May. Starting from 20th of May 2019, we have new definitions for the fundamental units of the international system. And because I told you that I will concentrate only on one of these breakthroughs or events that took place last year in the world of physics, I chose to talk to you in the end about the international system, but I don't know how much time do you still have. There is nobody from the organizers here. We are alone. This means we can do whatever we want, but I will not try to exhaust you. Let's talk a little bit about what the international system is and what are the changes which came into being this year. Of course, all of you learned in school about the fundamental units of the international system of weights and the measures. Why do we need such a system? Why did your physics teachers underline the importance of writing the correct measurement units for each physical quantity? Why do they insist? You?
Because I help scientists worldwide use the same units so they can communicate efficiently.
Very well. That's true. You know, until the 18th century, in different areas of the world, people used different measurement units. And in order to improve the commercial exchanges among different regions, they needed to measure the things with the same measurement units in order to improve the commercial exchanges. But we should note that the measurement units are one of the oldest tools created by humans, because they wanted to see how much they had, how much they lost, how much do they want to put in a transaction, how much material, how much wood, how many stones, and so on. So they invented measurement units for length, for time, for mass, and so on, in order to simplify the exchanges. And the history of this system of measurement units, which is called international system, started somewhere, I took as a starting point the year 1668, when it was the first try to define a measurement unit for length. So John Wilkins defines what he called a universal length, as well as the unit for volume and area, which are related to length. And he defined it as it is written there, as 38 Prasha Zoll, which in our language is almost 1 meter, 0.9937 meters, which is very close. And it corresponded to the length of a pendulum, having the small oscillations, having a semi-period of a second. The volume and the mass are defined accordingly, and not too long after that, that universal length is renamed, and you see that its value is slightly improved. Well, after that, France enters into the arena, and the French Constituent Assembly, 1 year after the French Revolution, and decides to create a system of units which is simple, uniform, and stable. And the other property is that it has to be simple enough to be used by everybody at any time, in any place. And they chose as a base unit for length the meter defined by Burattini. I showed you in the last slide. But because the pendulum had not the same length everywhere, in order to beat the second, they came back and defined the meter as 1 part in 10 million from a quarter of terrestrial meridian. So from the North Pole to the equator. The length of a meridian divided by 10 million was defined as a meter. And then things evolved. But what is interesting here, that in the same year, the National Assembly of France, which was, and it is now, the Parliament of France, they decided to create some etalon, some gauges, as I wrote there, for meter and grave. Grave was a unit for measuring mass. The transformation of that word gave us now gram. From, in French, is grave, the pronunciation. So it transformed as a word, and it became gram, we know today. And in 1799, the metric system was born. They created some etalons of platinum for meter and for kilogram, and they are deposited at the National Archives of France, and they were made in London, those etalons. Well, because I'm from Romania, I put here the date at which Romania adopted the metric system. It was on the 10th of September, 1864, date at which Romania became the 14th country adopting the metric system in the world. So afterwards, the meter convention was formed, and the International Committee and the General Conference of Weights and Measures. And these structures, these associations, and these institutions exist today. So their birth date is May 20, 1875. And in 83, Romania adheres to the meter convention. Well, in the picture you can see two of the etalons, the two gauges, one for mass, which is a cylinder of platinum and iridium, 10% iridium, 90% platinum, and the one for meter in the back. These prototypes were made in 1889, and because you learned in school that in order to have a system of units, you have to be able to express any physical quantity using only the measurement units defined in that measurement system. So in 54, the General Conference adopted the other three base units besides meter, kilo, and second, which was the ampere for electric current, Kelvin for temperature, and candela for the, somebody helping me, for the light intensity. Thank you. And in 1960, the name International System of Units, with the acronym, as in French, Système International, SE, was adopted. And in 71, finally, they adopted the seventh fundamental unit, which is the mole, the quantity for, or the measurement unit for the quantity of substance. Of course, I put there the last information that last year, only 4 countries on this planet are still not using the international system. UK, although partially it is used in day-to-day life, not in science. The United States, Liberia, and Myanmar. Okay, I will skip a lot of details from now on about related to the definition of each of the measurement unit. You can see the history of all the endeavor to define or to reach the best definition for meter. And I will stress only the present definition, which arose in 1983. And it is related to the distance traveled by light in vacuum and that tiny time interval. As you could recognize, that time interval is related to the speed of light in vacuum, because in 1975 it was fixed by definition, and it has that precise value. So the speed of light is not anymore measured. It is a fundamental constant. The kilogram, that picture shows you the way they kept the kilogram. That is that palace, which is called the Bureau of Measurements and Units. It is located, that palace, in Sèvres, which is a town very close to Paris. So that was the prototype of kilogram. And that prototype was retired last year. It was why? Because it was the only artifact. It was the only physical object defining a unit for measuring something, in our case mass. All the other units are related to physical constants. And this one was the only one, and it was very hard to get rid of it because of many things. One of them is that each country had a copy and still has a copy of this artifact, of this object. And periodically, each country had to come to Paris, to Sèvres, to compare their copy with the original and to see if their copy lost or gained mass, and to adjust its mass and take back in that country and be used for gauging, for comparing its mass with all etalons they had in that country. And nobody could say if the original or the copy lost or gained mass. They only adjusted the copies. Everybody supposed that the original preserved its mass, but it could gain or lose in 1 year, I don't know, 10 to minus 4, 10 to minus 6 kilograms or micrograms even. The measurements were very precise, and with all the safety reasons and safety measures, you see that the prototype is under 2 bells. Yeah, you see 2 two bells under which vacuum is made in order to restrict the possibility of atoms from air to adhere to the surface of the prototype and change even a little bit its mass. Regarding the second, the actual definition was given in 1967 and completed in 1997. And it is related to the period for the transition between the hyperfine levels of a fundamental state of cesium, which is an atom having the mass number 133. And this definition is still standing, and it was kept because it was related to a phenomenon which can be reproduced in any laboratory in each country, not only in one of them in France or in any other country. All countries having the same facilities can measure the same frequency, and with the help of that transition frequency in that atom between two excited states could give the second. So this is the main reason. If the original is destroyed, all the other countries can still measure the length of 1 second, the length of 1 meter, and the mass of 1 kilo, as I will show you. Regarding the amp, this is the old definition. I think you still have it in your textbooks, all of you, because textbooks do not change so fast. But in the future textbooks, when you learn about the unit for current intensity, you'll learn the new definition, hopefully. This is the old definition for Kelvin, as you learned it in school, which is not actual anymore. The candela kept its definition. This is the definition before 2018, and it is still the same. And also, this is the old definition of 1 mole, which will be replaced. And now about the big revision. What happened besides retiring the big K? This is the name of that prototype. You can say the mass prototype, aka big K. Yeah? The French are calling it le grand kilo. So in English is big K. After the retirement of the mass prototype, these 4 measurement units were redefined, and or their definitions have been revised or replaced. This information you already have. I put there a link to the official page or official website of the International Bureau of Measurements and Weights in Sèvres, and you can read a lot from there. How did they do it? Besides the values you have in the second column, they fixed the values for the constants in the first column. How did they do it? They did a lot of experiments measuring those constants, and when they reached the certain precision, they fixed the values. So now, Planck's constant has a fixed value, the electric charge has a fixed value, the Boltzmann number has a fixed value, and Avogadro's number. So they have no errors anymore, they are fixed constants. To see at a first comparison, at a glance, and all the differences between the old international system and the new one, you can see the relationship between between units used to define them, and in the past and nowadays. You see, for example, let's take one of them, the kilogram. The kilogram, if you look at the left-hand side picture, you see a gray dot with mpk. That is the mass of the prototype of kilo. With that, with the help of that prototype, it was defined the kilogram simply as the mass of that prototype. Nowadays, it is defined with the help of Planck's constant and second, which is the frequency for that transition, and speed of light, which means meter. They define kilo nowadays. The rest are similar. I will not go now into details because I think it's pretty late. I put here all the new definitions. Oh, I think I didn't succeed to put, I put here only 1 kilogram with numbers. I didn't put it for all the other units, but you can find them on the internet. What I want to tell you, and not to read anything about these slides, is that the attention and the interest moved from the definition of the unit to the role of the universal constants, the fixed constants. So now you can see the official definition of kilogram and ampere on this slide, and then I put here also 1 amp. It was very late, I don't remember what I did. And then nothing for Kelvin, for mole. And I think with this slide, it is best to conclude this presentation. Let's not call it a lecture. Thank you for your attention. So if you have questions related to anything I presented, you can go online and find some answers, and if not, you can write me an email. Okay? Until then, have a great lunch, I think.